Hello everyone, I'm Yaxin Zhou from Nanjing University of Aeronautics and Astronautics. I'm honored to attend this conference. The title of my report is Automated AADL Architecture Modeling, Leveraging Large Language Models for Safety-Critical Software. My report is divided into the 6 parts: background, preliminaries, research approach, experiments, prototype tool, and industrial case study, conclusion and future work. Safety. First is the research background. Safety-critical software refers to the software system whose failure could result in loss of life, substantial economic loss, or damage to the environment. Safety-critical software often needs to ensure reliability under strict constraints. Therefore, model-driven development has gradually become an important method to address the design and analysis of safety-critical software. For example, the extension document DO331 of DO178C provides guidance for model-based development and verification of urban software. In the field of safety-critical software, commonly used modeling languages include SDL, UML, SysML, ADL. Due to the increasing complexity of software, there exists a significant gap between software requirements and architecture models. Manually constructing formal architecture models for safety-critical software is challenging, as it relies heavily on the experience of engineers. To mitigate this intensive manual effort, Wang proposed a transformation from the requirement specification method based on a restricted natural language to ADL. Such templates reduce the ambiguity of requirements and enable a clear mapping to architecture models. However, this method has limited performance in generating complex models due to the limitation of transformation rules. With the rise of large language models, recently, there have been several studies on large language model-based model generation, which focus on conceptual modeling, taking requirements as input to generate corresponding models. These studies revealed that large language models can perform domain modeling tasks without supervised training on the specific task using carefully designed input. However, there is currently little research that uses large language models to generate AADL architecture models. Different from this work, our work focuses on AADL, a modeling language primarily used for software architecture modeling, which includes functional requirements. Safety require process not only depends on software requirements, but also considers a variety of design constraints. However, due to the lack of large-scale, high-quality AADL datasets for fine-tuning, we explore the potential of large language model in architectural modeling without supervised training. The second part is preliminaries. One of the most critical standards governing the development and certification of urban software system is DO178C, as shown in this picture. Software development under DO178C begins with the allocation of system requirements to software. Based on these inputs, high-level software requirements are derived. Following conformance checks, design constraints are introduced, and the requirements are further refined into low-level software requirements. The architecture analysis and design language is a textual and graphical language used to design and analyze the software and hardware architecture of embedded real-time systems. Our work focused on basic modeling elements, at least in right, such as thread, process, behavior annex, and so on. In order to use the large language model to generate the AADL architecture model, we need to learn some related technologies of the large language model. Promote, engineering, and R&D are two key technical methods that has emerged during the development of large language models. The third part is the research approach. The general workflow of our approach is shown in this picture. Our approach consists of three main stages. First, we decompose and refine high-level requirements and design constraints, mapping them to the proposed promoting framework (promote). Next, we explore the ability of large language models to generate AADL modeling elements. In this process, the first stage is used to evaluate the performance of three large language models under different promoting methods. The second stage focuses on generating complex modeling elements, such as moods and behavior annex with limited data, and conducts experiments around unshot promoting and the ID to verifying their ability to improve generation performance. Finally, multiple generated components and their attributes, connection relationships between components, constitute a complete architecture model. Feedback on the generated results is provided from evaluation metrics, and the model quality is continuously improved through multi-iterations. Note that the evaluation metrics focus on the generation aspect of large language models, ensuring the production of high-precision architecture models. In order to facilitate the accurate analysis of requirements and architecture modeling by the large language model, we reuse the restricted natural language template proposed in previous work, which can reduce ambiguities of natural language without changing the requirements writing habits of software engineers. Specifically, a template usually consists name, type, input, output, composition, and various constraints. This template maps the high-level software requirements and design constraints to different modeling elements of the software architecture, such as components, pods, data flows, and other key elements, through fields such as composition, functional requirements, and performance requirements. For each category of requirements shown in last table, a set of general restriction rules in this table are designed to constrain the use of natural language. For example, R1 is to ensure the feasibility of hierarchical modeling and behavior modeling. To better understand this template, we take the injection control set process as an example and provide a detailed description, where the green font A uses limited natural language rules, such as data processing module sends launch signal to this module. Based on our template, we design a promote consisting of a task description, the restricted natural language template, naming conventions, and output constraint. For generating an AADL architecture model, the purpose of the task description is to guide the large language model in clearly identifying the type requirements of the AADL architecture model to be generated, and to generate the model according to the given naming conventions and output constraints. The naming convention is used to standardize the naming of components, features, and connections. The output constraints to regulate the model's output. To enhance the performance of large language models in generating complex models, we conduct experiments using unshot and AADL approaches for comparison. In the case of unshot learning, an example are provided as input-output pairs to the large language model to learn the desired output format and content. To facilitate this, we add modeling requirements and reference model example based on the ANL mode. For the AADL method, we integrate a large language model with the Liang chat framework, embedding model and knowledge base, and we choose BGE as the text embedding model in the AADL experiments. At the same time, we organized knowledge related to flows, moods, and behavior annex and construct it as the content of the knowledge base. The last part of this section is our method evaluation section. Inspired by the method of Chen, the AADL texture model is classified by modeling elements and the scores are assigned. And we propose the definitions and the equations for evaluating the precision, recall, and RV score of the AADL texture model. M and N denote the total number of modeling elements in the generated model and the reference model. In the experimental part, we first propose the three experimental questions. First, how do large language models perform on AADL modeling element generation? Second, based on question 1, how can we further improve the performance of large language models in generating AADL complex modeling elements, such as moods, behavior annex? Third, how does the proposed method perform in generating a complete AADL architectural model? To answer these questions, we use different large language models: GPT-4, DeepSeek V3, GM4+. In terms of promoting methods, we choose general promoting, where tasks and requirements are expressed in free text, as well as the previous mentioned promotes and unshots. In order to evaluate the performance of large language models in generating AADL architecture models, we collect AADL models related to safety-critical domains from the GitHub of the AADL standard and the offset and blur tools. Finally, we compare 55 requirements and their corresponding AADL models. To answer question 1, we use 3 large language models, 35 component requirements, and 2 promoting methods. The experimental results are as follows. We can see that after applying ANL promotes, the F1 scores of all 3 large language models improve to varying degrees. Therefore, for question 1, large language models have certain capabilities in generating different modeling elements. Compared to the standard promote, using the ANL promote improve the performance of the 3 large language models in generating AADL modeling elements. During the experiment, we found that GM4+ performs slightly worse in the 3 modeling elements, flow, mood, and behavior annex. Based on the findings from question 1, GM4+ performs poorly on modeling elements such as flows, moods, and behavior annex. To address this limitation, experiment 2 aims to enhance GM4+ ability to handle complex model elements under data-constrained conditions. The experiment evaluates GM4+ in a zero-shot in a zero-shot setting using 15 component requirements and compares its performance against N-shot learning and ID enhanced GM4+. From the three figures, we can see that both N-shot and ID improve the performance of GM4+ in generating complex modeling elements, but N-shot performs better than ID. However, we lack sufficient evidence to claim that adding two samples to the promote is more effective than adding one. Finally, we evaluate the performance of our proposed method in generating complete AADL architecture models to answer question 3. The table shows the score of various metrics of 3 large language models in generating 5 complete architecture models. It can be observed that the F1 scores of the 3 large language models in each model are above 0.84, especially GPT-4 and DeepSeek V3 achieving an F1 score of up to 0.94 in the FCS models. Overall, GPT-4 and DeepSeek V3 perform stably, while GM4+ has a slight advantage in specific models. From the experimental results, we can derive the answer to question 3. GPT-4o and DeepSeek V3 exhibit comparable model generation quality, while GM4+ performs slightly less effectively. However, they are still empirical for fully automated architecture modeling. Currently, the overall model architecture generated by large language models is generally reliable, but errors may still occur in the details, such as syntax errors and port type errors. Therefore, considering these detailed issues, and we believe that large language models are more suitable at the current stage as modeling assistants to support the completion of modeling tasks. Based on the above experiments, we implement a prototype tool. The prototype tool for large language models-based AADL architecture modeling, called Large Language Model for AADL. It is implemented based on Java and supports GPT-4, DeepSeek V3, and GM4+. The tool is developed within the offset plug environment based on the Eclipse platform. The tool consists of 3 modules: entering detailed component requirements and design constraints, selecting a large language model to generate an AADL architecture model, and importing the generated results into an AADL field of offset. Finally, a graphical AADL model can be obtained. We successfully applied this tool to the injection seat control system. The system is a safety-critical software system that provides real-time monitoring, multi-mode control, and ensures pilot safety. In this case study, the large language models for AADL tool generates different components, such as system, thread, device, and so on, based on the tool. In addition to generating the basic architecture model of the system, related design constraints can also be generated, such as timing, component binding. The relevant AADL is shown below. Based on these components and design constraints, with some manual modifications, the textual model can be converted into a graphical representation. Finally, there are conclusions and future work. In summary, we propose a large language model supported method for AADL architecture modeling and introduce the promote framework to enhance modeling accuracy. Comparative experiments show that the unshot approach is more effective than IID in improving complex component generation. Finally, we implement the large language model for AADL prototype to demonstrate the practical applicability of our method. Our future work focuses on the decomposition and refinement of requirements, as well as the automated construction of RNN promote. We also plan to explore structured output generation and indexing for ID pipeline, and conduct compositional verification of AADL architecture models. That's all. Thank you very much.